So types of radioactivity. Curie was focused on finding different radioactive elements. Ernest Rutherford, whom we've heard about in terms of other experiments, and others were focusing on what is radioactivity, what are the characteristics. So they found that the nuclei of radioactive elements are unstable, and they spontaneously decompose. They're essentially falling apart. And they do this by emitting small pieces of themselves in order to become more stable. So categories of natural radioactivity include alpha decay, beta decay, gamma-ray emission, positron emission, and electron capture. So they started out with the Greek letters alpha, beta, gamma, and then I don't know what happened. So let's review nuclear symbols. You should have learned this in Chem 1A. So this is a nuclear symbol. Here, the capital X is representing the chemical symbol. That's the 1 or 2 letter abbreviation for the element. On the left is a superscript, is the mass number. That's the number of protons that element has. And as a subscript on the left is the atomic number. I got that backwards. The mass number on the top is protons plus neutrons. The atomic number is the number of protons. Okay, so here's mass number and atomic number. The atomic number, I personally think, should be A, but it is not. It's Z. So the number of neutrons is the difference between these two. So the atomic number, that's backwards. No, it isn't. Sorry. The mass number minus the atomic number. I hate those letters. I really hate those letters. Most elements have several different isotopes. And isotopes differ in the number of neutrons that are present in the nucleus. So a particular element, every single atom has the same number of protons, but the number of neutrons may differ. So if we're talking about a particular isotope of an element, we call that a nuclide. So we can identify a particular isotope or a nuclide by the element name or symbol followed by the mass number. I'll just do an example here. So carbon-14, the nuclear symbol is this. That's a bear on a computer to type in, because you have to pull out the equation editor to do the stacked superscript subscript. That's a pain. And how do you read it anyway? So we can call it C14 or carbon-14. And those are easier. What we need to specify is the mass number. We don't really need the atomic number, because if we want to know what that is, it's the same for all carbon atoms. It's 6. It's on the periodic table, right? And no good chemist is ever without a periodic table. We can also represent the main subatomic particles with nuclear symbols. So the proton is a P, and the superscript over here, the mass number, is a 1, because the total number of protons and neutrons in a proton is 1 proton, right? And here the atomic number would be 1, because there's 1 proton, right? So a neutron is going to have a mass number of 1 and an atomic number of 0, because there are 0 protons in a neutron, right? And that's N for neutron. And then there's the electron. Electron has a mass number of 0. It's like, okay, we can deal with that, because they're so small they don't really have mass, right? But then how does it have -1 protons? So we'll get back to that later. Let's look at alpha decay. And you do need to know what these different types of decay are. So alpha decay, the nucleus is emitting a particle that we call an alpha particle. And an alpha particle is a helium nucleus. So this is the symbol for an alpha particle. Helium, 4 protons, a total of 4 protons and neutrons, mass number of 4. It's got two protons. So it's got 2 protons and 2 neutrons. This is identical to a helium nucleus. Okay. So we have the original nucleus, and it decays by spitting out a particle composed of 2 neutrons and 2 protons. We can write nuclear equations that represent the nuclear processes that happen in decay, such as radioactivity. So these are a little bit different than regular chemical equations. We're going to see the nuclear symbols, and we are looking here not at the number of uraniums being the same on both sides, because this is nuclear chemistry. And in nuclear chemistry, one element can change into another element. So nuclear chemistry was the exception to a bunch of the laws that we had. So what we're conserving here is mass number and atomic number. So the sum of the mass numbers on each side has to be equal, and the sum of the atomic numbers on each side has to be equal. So here we have 92 on the left. 90 plus 2 is 92 on the right. The mass number is 238, and over here we have 234 plus 4. So that's what we're looking at. In nuclear reactions, the elements often change their identities. And so you can have, here we have uranium changing into thorium. And that's okay in a nuclear reaction.
Question.
Yeah.
So if you have, if you know which the parent nuclide is and the daughter nuclide is, then you can determine the
yes.
type of decay?
Yeah. So if you know that this is the parent nuclide and that it's undergoing alpha decay, you know what the alpha particle is, and so you can figure out what the mass number and the atomic number of this daughter is. And from the atomic number, number 90 on the periodic table, you go find it, and then, oh, it's thorium. And that's how you know what the element is. So the parent is the original one, and it decays and forms the daughter. I'm not sure why it's a daughter instead of a son, but that's what they call it. Okay, so let's write the nuclear equation for the alpha decay of polonium-216. So we start this by writing the nuclear symbol for polonium-216. So that's PO. 216 is the mass number. That goes as the superscript. We'll find polonium on the chart, and it's element number 84. So 84 is the subscript. So the way I remember this is it's always the larger number on top and the smaller number on the bottom. And if you just subtract those, you get the number of neutrons. So it's like it's stacked up for subtraction. So there's our parent. And alpha decay, now they often write the daughter nuclide first and then the alpha particle, but you don't have to do it that way. So alpha decay means that an alpha particle is being emitted, and that is a helium nucleus. Plus, now we're going to do the element symbol last, and the math here is very simple. The total is 216. I've got 4 plus something is 216. So it's 212, right? Don't overthink this part. Here's 84. 2 plus what gives me 84? Well, it's 82. And then I look on the periodic table and I find element number 82. It's lead. And so that's the symbol. Question?
So then that helium is always present in alpha decay? Or?
Well, it is a helium nucleus. Okay. The same as a helium nucleus. It's not actually helium. Okay. But that is what alpha decay is.
Okay. Are there any other types of?
There are other types of radiation that give off different particles, but they are not alpha decay. Okay. Alpha decay is always that alpha particle. Yep. Any other questions? So we use an analogy with vehicles to help us remember how some of the characteristics of the different types of radiation. So we have ionizing power. Ionizing power is the ability of radiation to ionize other molecules or atoms. So you get bombarded with radiation, it can cause the molecules in your body to become ions. Is that going to mess up the chemical reactions occurring in your body? Yes, it's not good for you, right? So ionizing power, something that can ionize molecules can cause damage to living organisms. Okay, it damages chemical reactions, can result in cells dying or reproducing abnormally. It's just not good for living things. So alpha radiation is like the 18-wheeler truck of radioactivity. It's a large particle. It's the most massive particle of all of the forms of radiation. It has the highest ionizing power. So ionizing power is like being hit by a truck, right? Just smashing things. So the 18-wheeler can do a lot of damage that way. Penetrating power is when that particle can get through other objects. So how far it can penetrate through something else.
If it's bigger, should be lowest.
Yes. So the big truck, this would be like vehicles trying to get through stop-and-go traffic. So that 18-wheeler truck, when there's just lots and lots of traffic around, he can't do very much. He just has to sit there and wait. Right? He can't just change lanes and zip around. So very low penetrating power. But when it does get to a living organism, it causes a lot of damage. So low penetrating power, high ionization power. Penetrating power is defined as the ability of radiation to penetrate matter. So with the low penetrating power of alpha particles, they can be stopped by a sheet of notebook paper. They can't get through that. Your clothing will stop them. Some air can stop them. So they can't get through stuff very easily. So if they are outside your body, it's relatively safe. Even if they contact your skin, they're only going to be able to damage what's on the surface of your skin, right? But if you inhale alpha particles, or you ingest something that is giving off alpha particles, and now they're in your body, then they're going to be very dangerous because they do have high ionization power. So the second category is beta decay. It's the Greek letter beta. And in this case, an unstable nucleus emits an electron. Now, does that bother anybody? The nucleus emits an electron. Wait, what? That's exactly what I expect. Because there aren't electrons in the nucleus. So how does this work? Well, it turns out that a neutron can come apart into a proton and an electron. So a neutron is actually a combination of a proton and an electron.
In addition to the electrons that...
Yeah, this is nothing to do with the electrons that are outside the nucleus. This is an electron that's coming from inside the nucleus.
So is a neutron just kind of been like the lie? Is it really just kind of...
Well, that's an excellent question. Is a neutron a lie? It's actually all a lot more complicated than we've led you to believe. We've lied to you.
Yeah, we should be used to it by now.
You should be used to it by now, yeah. But this is the reason for the -1 as the atomic number on an electron. A proton and an electron, you put their two atomic symbols together, and you end up with 1 as the mass number and 0 as the atomic number. Because you've got a 1 and a -1, those add up to 0. Right? Yeah, sorry. So it's very convenient and nice to think that there are 3 subatomic particles, protons, neutrons, and electrons, and that they're always the same and that they can't be divided or broken up, and that's not true. And besides those 3, there are lots of other ones. There's muons and pluons and all kinds of other things, which I personally don't care about at all, but they are there. So in beta decay, one of the neutrons becomes a proton and an emitted electron. So the electron coming out is the beta radiation. So when we look at beta radiation, or the equation for beta decay, you're starting with your nuclear symbol for the parent, and the decay particle is the electron. And what you do is the same thing as before. Okay, this was a total of 228. I've got a 0 here, so this must be 228. This is 88, and I've got a -1. This must be 89 now. And so radium becomes actinium, which is actually 1 higher in atomic number. Any questions? So in our traffic or vehicle analogy, beta radiation is a 4-door sedan. Less massive than an alpha particle. So lower ionizing power. When it smashes into something, it doesn't do as much damage. But it has higher penetrating power than the alpha particle. A 4-door sedan can move through a traffic jam easier than an 18-wheeler can. So beta decay can be stopped by a sheet of metal or a thick piece of wood. Your clothing or a piece of paper is going to do nothing. It'll just go right through that. But a thick piece of wood will stop it. So this is more dangerous than alpha radiation outside the body, but it's less damage inside the body than alpha radiation, because its ionizing power is less. They're both bad, though. Next one is gamma ray emission. And this is not a particle. So it's a gamma ray. It's a form of electromagnetic radiation. If you remember back to the electromagnetic spectrum, the thing that's way up at the high energy end was gamma rays. This is the radiation. They are high energy photons. Has no charge, no mass, and so the mass number and the atomic number of the parent nuclide doesn't change. Gamma rays are usually emitted along with other types of radiation. So it's got the symbol, the Greek letter gamma, 00. So just gamma ray emission is not going to change the parent nuclide, but it usually happens with other things. So an example of this would be uranium-238 undergoing alpha decay and also gamma ray emission. So you fill out the equation the same way. The zeros here on the gamma radiation aren't going to do anything. So gamma rays are the motorbike or motorcycle of radioactivity. Lowest ionizing power. So motorcycle smashing into something doesn't do as much damage as a 4-door sedan. But a motorcycle can go through rows of stopped vehicles, right? And it can penetrate and get through. So it's got the highest penetrating power. It can be stopped by several inches of lead. Several inches of lead, that's a lot of lead. Or really thick slabs of concrete. But gamma radiation just pretty much goes through most things.
So what's worse, the gamma rays or having that much lead around you?
Well, as long as you're not licking the lead shielding or something, the lead itself is not going to cause you any problems unless you're, getting it, on your food or licking it or somehow.
Which type of radiation?
Well, it depends.
So then do gamma rays accompany alpha and beta always, or is it sometimes?
That's a good question. Alpha rays do not always accompany alpha and beta emission. Sometimes they do. And we're not going to expect you to know when they do or when they don't.
Distinguish what would be an alpha decay, beta decay?
So you would be told, write the equation for the alpha decay of this thing accompanied by gamma ray emission. And then you'd put the symbol in there. And that's something that, it's very difficult to predict what's going to happen, and so it's more just a matter of they've done experiments and they know that this is what happens.
No ionization on gamma either?
Gamma has low ionizing power. So it doesn't do as much damage, but it can get through almost anything and do its damage. Oh, sorry.
Yeah, it's okay.
You're too close. I can't see you.
Do certain radioactive elements have a type of radiation they normally emit?
Yes. Yeah. Certain radioactive elements, certain nuclides, do have a particular type of radiation that they emit. And they will do that pretty much all the time. Yeah. And I'm not going to make you memorize those things. So uranium-238 does alpha decay and also emits gamma radiation. And the reason that I can say that to you is I'm looking at the equation right here. I don't remember all of these things either. Positron emission. So positron is a word that kind of sounds like electron, right? Electrons are negative, and starts with pos, like positive. So a positron is an anti-electron. It's an antiparticle. So if you've watched or read any science fiction, they talk about matter and antimatter, right? Matter and antimatter, you put them together, and what do you have? Nothing, right? They like cancel. It's matter that cancels each other out. It's crazy. Positrons and electrons do that. So a positron has the same mass as an electron, but an opposite charge. And if a positron collides with an electron, the two particles annihilate each other. Is that crazy or what? It's not that nothing happens, though. You get energy released, and the energy comes in the form of gamma rays. So in nuclear chemistry, matter is not conserved, energy is not conserved, but if you put those together, matter plus energy is conserved. In positron emission, a proton is converted into a neutron and emits a positron. So we take the proton, and that can come apart into a neutron and an emitted positron. So this is kind of like but not like the electron plus the neutron, no, electron plus the proton being the neutron, right? Yeah, it's fun to keep that straight. So when an atom emits a positron, the atomic number decreases by 1. So here we have phosphorus 30, and the mass number is going to stay the same, but the atomic number is going to go down to 14. Positrons are similar to beta particles in terms of ionization and ionizing and penetrating power. They're the same mass as an electron. So they're going to have similar penetrating power and ionizing power.
So what happens when a proton and a positron come into contact? Is that like some new stuff right there?
Well, a proton and a positron, they'd probably say hi. Hey, how you doing? I don't know. And then, pardon me?
Thinking about it, if they're both positive, they probably wouldn't get
They'd probably repel each other. Yeah.
And since they're so small, positrons are pretty much just going to get buoyed.
Yeah, it'll just kind of bounce off, probably. So the last one is electron capture. So this is not something being given off, but this is something coming in. So a nucleus assimilates an electron from an inner orbital of its electron cloud. So one of those 1s electrons, most likely, gets absorbed into the nucleus. So how does an electron exist in the nucleus? Well, it combines with a proton and becomes a neutron. So that's the net effect. You've converted a proton into a neutron by absorbing an electron from one of the inner orbitals. So here we've got ruthenium-92, electron capture. So it's capturing an electron, add an electron to it. Predicting these products, even though all of this other stuff is like kind of trippy, it's just adding and subtracting. So 92 plus 0 equals 92. 44 plus a negative 1 is 43. Look up element number 43, symbols TC, technetium. Here's a table just sort of summarizing all of this. These symbols of alpha, beta, gamma, what the changes are and examples, and so that is a nice reference. Okay, let's write nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235, followed by beta decay of that daughter, and then another alpha decay. Right? This will be fun, right? All right, if you say so. Okay, uranium-235. This is not that bad at all. Uranium-235, well, I should make that a capital. Obviously, a capital U. So uranium-235, we find it on the periodic table. Where did you go? Over there, 92. I was looking on the wrong side. Okay. So it starts with alpha decay. So alpha decay means we're going to draw an arrow here, and it's going to lose an alpha particle. Same symbol as a helium nucleus. So then we do the math. The mass number must be 231, and the atomic number must be 90. So that 90 plus 2 is equal to 92. 231 plus 4 equals 235. So then I find element 90, and that's thorium, TH. So that's the first one. The second one is that daughter, the thorium-231, undergoing beta decay. So what's the symbol for a beta particle? 0, -1, E. It's an electron. So then we're just going to do the math again. 231 is still the mass number. And now the atomic number is 91. Because 91 and -1 is 90. And so that's in the middle. That's PA. And I'm blanking on what its name is. You can do this without knowing their names. And then another alpha decay. So 231, 91, PA. Alpha decay, so we've got another alpha particle. And so 231 minus 4 is 227. And 91 minus 2 is 89. And element 89 is AC, actinium. Any questions? Writing the nuclear equations is mostly memorize those symbols so that you know what the symbol for beta decay is. Let's see if we can finish this before my iPad dies. Write the nuclear equation for the positron emission of sodium-22. So we start with the nuclear symbol for sodium-22. Got Na22. We look in the periodic table, and the atomic number is 11. Positron emission. What is the symbol for a positron? It's the same as an electron, but the charge is opposite, right? So it's E0 plus 1. We usually put the plus there just to say, yeah, we mean the positron is positive. So then the mass number is going to be the same, and the atomic number is going to be 10, and so that's going to be what? Neon. Okay? One more. Electron capture in chromium-76. Not chromium, krypton. I don't know what's wrong with me today. Krypton-76. So that's element 36. Electron capture. So now we're going to add an electron. Instead of one like this where an electron or a positron is emitted, we're going to put one in. So plus 0 minus 1. So we have 76 up here, and then we've got 35 down here, and so that's bromine. Any questions? Yes.
So unless otherwise specified, we would assume that it's emission.
Yes, if it says alpha decay, beta decay, those are all emission.
Or even like positron emission, unless otherwise.
Yeah, if it said positron decay, that would also be emission. So electron capture, the term is distinct from beta decay. They both involve electrons, but beta decay is the electron coming out, electron capture is coming in.
And then to clarify what you're talking about, like the symbols,
Uh-huh.